Any chemical reaction where you can look up these delta H sub F values, you don't even need to do a calorimetry experiment anymore. Now, a good question you can ask yourself now is, why do we even do calorimetry experiments? Well, that's how these numbers came from. Okay, somebody had to do that, and they did a calorimetry experiment to get these delta H values. But once you've got them, they're tremendously powerful, because now we can use the fact that delta H is a state function, and we can use the fact that it doesn't matter the conditions that I got to that number. All that it matters is what the number is, and I can go and calculate what delta H is. So let me tell you how this works. We'll start out with a generic reaction. AA plus BP yields CC plus D. And the way this works is we can find the enthalpy of any reaction under standard conditions. So delta H reaction is I don't know. What we can do is we can take the enthalpies of formation, which we can look up in a table, and we can express them as, before I do the sigma sign here, let's do it this way. We can say that delta H reaction equals delta H of formation final minus delta H of formation initial. Remember, the delta H, whenever you see a delta, that means final minus initial. So what does that mean in terms of this equation? What that means in terms of the equation is final is products and initial is reactants. Okay? So we can take any chemical equation that we've written and we can write down delta H, which we've looked up in these tables, of the products minus delta H of the reactants. Now this equation is not quite correct yet. So let me fill out the last set of details. It's actually the sum of the products. So a sum is a capital sigma sign minus the sum of the reactants, because you have multiple things in the reactants and products. So let me give you a real chemical reaction instead of just this A's, B's, and C's. So let's take hydrogen gas plus O2 gas forms H2O. This is one of our problems we like to do, right? Delta H reaction, don't know what that is. Okay? Now, first thing we need to do is balance this equation. You need, absolutely 100% need a balanced equation in order for this to work. So I've got two hydrogens here, two hydrogens here, two oxygens here, only one here. So I'm going to put a 2 there, and I'm going to put a 2 there. Okay? Now we have a balanced equation. So how does this work? Delta H reaction is equal to the sum. Now here's the other little piece that I didn't put in here. The number of moles from the coefficients out in front, delta H sub F of the products, minus the sum, number of moles, delta H sub F, that you look up, of the reactants. All right, and you're still probably thinking, what does this mean? This is what this means. That M is related to the coefficients out in front of the product side, and the N here is related, that N is related to the coefficients in front of the reactant side. Okay? So let's write this out more explicitly so you know what I'm talking about. All right, I just lost the N. Let's get that guy back. Okay, so let's write it for the equation I've just written. Delta H of reaction is equal to, I usually do these in big brackets now, 2 moles H2O times, now what you got to do is you got to look up H2O liquid. This comes from the table. That's delta H sub F. Okay, so this is going to be delta H sub F of H2O liquid minus 2 moles H2. I'm not going to write it this much on the next problem, but I'll just give you an idea. Times delta H sub F of H2 gas plus, apologize for this, let's do it this way, plus 1 mole delta H sub F of oxygen gas. Okay, now if you've been paying attention and you just kind of see where I'm going with this, you're going to recognize something, and that is delta H sub F of hydrogen. Oh, wait a minute, hydrogen is, that's 0, right? That's the pure elemental form of it, and so is oxygen. So those two are both 0. We can look them up in the table. O2 gas is 0. This guy right here is minus 285.8. Where does that come from? This is kilojoules per mole. Where does that come from? That's that guy right there. All right, so I'm just going to rewrite this. Delta H of reaction is equal to 2 moles times minus 285.8 kilojoules per mole minus 0 plus 0. Moles cancels moles. I'll get my calculator out. It's actually my phone. 285.8 times 2 is minus 571.6 kilojoules is delta H reaction. Okay? So what we've done is we've written down some chemical equation, we've balanced it, and then what we've done is we've figured out what delta H for that reaction is without doing a calorimetry problem. We've just looked stuff up. Now, as I mentioned to you before, somebody had to do the work. I mean, somebody had to do calorimetry to make this table. But once it's done, this is an amazing resource. Okay, they've saved you a ton of work. So how do we do this again? We took the sum of the product of moles times delta H for each thing, and products minus reactants. This gives us delta H reaction. Now look, you said, well, you might be saying, well, look, this is oxygen, is 0, hydrogen, is 0. This one is not too difficult, right? No. Let's do a little more complicated one. And I'm going to do one that's not super complicated because I'm balancing it in front of you, and I don't want some ridiculous one. I actually don't have any notes in front of me either. So let's slide this guy over. Let's get rid of all this. All right, and I'm going to get rid of all this. Just cleaning up my screen here a little bit. Okay, and then don't like this arrow right here either. All right, let's do a little bit more complicated problem. Not a lot more, just a little bit more complicated. So let's take this equation. Let's take a combustion reaction of methane plus oxygen, and the products for this are CO2 plus water. Okay, and let's pretend I use gas phase water. I could have used liquid phase water as well, but they're going to be different delta H values depending on which one I chose. All right, so let's balance this. There's one carbon, 4 hydrogens, 2 hydrogens, so I need a 2 out in front here. So I'm going to do carbon 1, hydrogen 4, oxygen 2, carbon 1, hydrogen 4, oxygen 2 plus 2 is 4. So that's just going to be a 2 out in front of the oxygen. Okay? Have to balance the equation before you can attempt this using this. All right, so there's my balanced equation. Delta H sub F is equal to the sum number of moles delta H sub F products minus the sum number of moles delta H sub F reactants. Okay, so let's just write down what those are. Big brackets here. I've got 1 mole CO2 times, where's CO2? In fact, I'm just going to highlight the ones I'm interested in. CO2 gas is right, whoops. CO2 gas is right here. Water, H2O gas, is right here. CH4 is right here. Let's help me find it in a minute. And then oxygen, oh wait, that one's 0. We already knew that. Okay, so 1 mole CO2 times minus 393.5 kilojoules per mole. Moles cancels moles. Plus, remember this is the sum, so I'm going to add everything on this side. 2 moles H2O times H2O gas is minus 241.8 kilojoules per mole. Okay, that's the product side. And now I'm going to subtract the reactant side, which is 1 mole CH4 times minus 74.6, I think that's what that says. Yep, 74.6 Denmac kilojoules per mole, minus or plus 2 moles O2 times 0 kilojoules per mole, because remember that's the element in its most stable form. Moles cancels moles, moles cancels moles, moles cancels moles, and this whole thing is actually equal to 0. All right, so this guy right here is the products, the sum of the products, and this guy right here is the sum of the reactants. All right, so what does that all end up equaling to? Delta H sub F is equal to, now I need to get my calculator out, minus 393.5 kilojoules plus, let's see, 2 times 241.8 is negative 483.6. Now, caution, there's a plus sign right here, there's a negative sign right here, and there's a negative sign right here. You've got to keep track of these negative signs. In fact, what I'm going to do right now is I'm going to get rid of that plus sign to remember it's a negative 393 and negative 483. Okay, that's the hardest thing about this, is keeping track of these negative signs. Now, again, I've got a negative in front of this entire thing, but the guy inside of here is a negative. So this is like minus 74.6. Okay? Minus and a minus, so be careful about this. This is minus 383.5. This whole thing is minus 867.1 kilojoules. And this is plus 74.6 kilojoules. This whole thing is going to be minus 792.5 kilojoules delta H sub F. Or, excuse me, delta H reaction. This should be reaction. All right, what's that telling us? Well, first of all, it's a negative number. It tells us it's exothermic, and it should be, right? It's a combustion reaction. This is methane gas burning in oxygen. If any of you has a gas stove at home, that's the chemical reaction that this is doing. The combustion, the burning of methane gas. If you hold your hand up next to it or you put a pot on top of it, it gets hot. So it makes sense that it's a negative number. It also makes sense it's a pretty big negative number because combustion reactions are very exothermic reactions. The other thing we get from this is we do not have to do a calorimetry problem. We can just look these things up in the table and use this standard enthalpy of formation calculation to figure out what any reaction is.